So last time we introduced not sure how many pen can trust. You want a pen or pencil? Okay. I have also pen just in case. Okay, Sophia, how do you pronounce this name?
L'hôpital.
Okay, the L'Hôpital. Okay, so there's no S, there's no H because of French. Eh, Sometimes they use this S instead of the cap, but they read the same. L'Hôpital, not the hospital. Okay, there are two basic cases for this rule. So it applies to indeterminate. It applies to indeterminate forms and it only applies to this form. If it's not the indeterminate form, it's not applicable. It's the only thing it applies. So there are several types of indeterminate forms. The first type, 0/0. It means both the numerator and the denominator for the limits if this condition satisfied, then we have the L'Hopital rule. Limit of the quotient. Limit of the quotient of the derivatives. Okay. Second type. This is when okay, so this is the second type of this indeterminate form. If the limit is of this form, we have the L'Hopital rule. Okay. In this process, we would expect this limit becomes easier. So we apply L'Hopital rule to make the limit easier, but they have the same limits. Typical example. The first one we had is for this one is the indeterminate type, indeterminate form, so we can apply L'Hopital rule. I will use LH for L'Hopital. So it confirms what we have done before using a different method. The confirmation. Sophia, do you remember what method we used at the beginning for this limit?
Please, L'Hopital rule?
So before that, we
Oh,
found this limit.
we used the geometric
Yes.
proof.
Okay, so at the very beginning, we found this limit using the geometric method. We compare the arcs. So here it's a confirmation, but we shouldn't use this as the method to find the limit, because in this process, we used the derivative of sine is cosine. In order to find this derivative, we need this fact. We cannot use something that is based on the result. Okay, so it's just a confirmation, but we shouldn't use this as the way to find the limit, because in this process, we already used this fact. But we do have something new, limit. But this one is something new. We found the limit is a L'Hopital rule, because again, it's the indeterminate form. When x goes to 1, logarithm goes to 0, x minus 1 goes to 0. It's indeterminate L'Hopital rule. Okay, Sakina, what's the derivative of logarithm x? Yes, 1 over x. And this is 1, so it will be 1 over 1. Okay, so for these two types of indeterminate forms, 0 over 0, infinity over infinity, we can apply the L'Hopital rule directly. The limit is the same as the limit of the quotient of the derivatives. In some cases, it's not this form, but we can convert it to these two types. Type 3. This time we'll deal with the product. That means we're dealing with limit of the product of two functions. So one of them go to 0. But the other go to infinity. So one goes smaller and smaller, the other one goes bigger and bigger. There's a competition between the two. Which one dominates? This one goes to 0 faster then this one go to infinity, the limit will be 0. If this one go to infinity faster than the speed of this go to 0, the limit will be infinity. So which one dominates? So in this case, we will convert this to one of the previous types. So approach, convert. Okay. Instead of doing the product of two functions, we keep one on the numerator and we put the reciprocal of the other one on the denominator. In the end, it will be the same. Now it's a quotient. Or we can keep the second one on the numerator, put the reciprocal of the first one on the denominator. Again, it's the same. Now let's check what's the type of the first one. Sophia, what do you say about this type? It's a quotient.
Yeah.
fx 0. What about 1 over gx?
Infinity.
So 1 over infinity, what do you say about this one?
0.
Yes. So this time, both the numerator and denominator equal to 0. So we have the type. And Sakina, what do you say about this one? Is this an indeterminate form? If it is, what's the type? What do you say about the numerator? Go to infinity. What about the denominator? So fx go to 0. What about 1 over x, fx? It's infinity. This one becomes smaller and smaller. So this whole thing becomes bigger and bigger. Both numerator and denominator, they go to infinity. So it's the type infinity over infinity. So instead of finding the limit of the product, we cannot plug in. We want to apply the L'Hopital rule. So we make the conversion, convert the product to the quotient of 1 with the reciprocal. Then we have these two types. We can check if we pick one that's easier, we apply the L'Hopital rule. A typical example is the following limit. Okay, so here we have this x go to 0 plus. Sophia, what does this mean?
X goes to 0 from the right.
Okay, so it means x goes to 0 and x is positive, goes to 0 from the one side. Because in this definition, logarithm, x has to be positive. Now, this x goes to 0, but the logarithm of this goes to negative infinity. So it's this type. We want to convert this to either this one or 0 or infinity over infinity. Two choices, we see which one is easier. Two choices. We convert this to x over the reciprocal of logarithm, or logarithm over the reciprocal of x. Sophia, what's the type of this one?
It's 0 over 0.
Over 0. Sakina, what's the type of this one? So when x goes to 0, this goes to negative infinity, this goes to positive infinity. So this will be type infinite over infinity. Which one is easier? Okay, so Zichen, you know which one is easier if you want to apply the L'Hopital rule? The bottom one. The bottom one, because over here is logarithm, we know what the derivative is. But if you go with this, it will be 1 over logarithm square. It will make the limit more complicated. So we prefer this one. We will continue with this limit. Before we apply the L'Hopital, we'll do the conversion first. Now we are in the right type, we can apply the L'Hopital. Derivative 1 over x, 1 over x squared. Simplify negative x is 0. So in this way, we find the limit of this is 0. Okay, that's the third type, limit of the product. The next type, the limit of difference. Oh, I'll go with that means we're looking for this limit. So we want to find the limit when both f and g go to infinity. Well, no, which one go to infinity faster, or are they comparable? Typical example. Let's go to Sakina. Here we have x go to power 2 minus. What does this mean? Okay, so we go to power 2 from the left. On that side, we know that secant 1 over cosine. Cosine go to 0 from the positive side. This will go to infinity. Tangent x also is go to infinity as x approached power 2 from the left. So it's this time. To find this limit, use the definition. We can write the difference as the quotient in the common denominator. So from a difference to a quotient. When x goes to power 2 from the left side, go to 0, sine goes to 1, so 1 minus goes to 0. Now it's the type 0 over 0. We can apply the L'Hopital. Yes, Sophia. Okay, maybe not. Okay, so this is the limit. Negative sign, so negative cosine, cosine negative sign. We apply L'Hopital. Okay, now let's check this limit. What should we do from here? Sophia, what would you do from here? How to find this limit? Parabola 2. What's the cosine parabola 2?
It's 0.
Sine parabola 2.
It's 1.
And so what should you do to find this limit?
You can plug it in.
Yes. So now we don't have to apply L'Hopital rule because it's not indeterminate anymore. It's just a 0/1. Okay, we find the limit. And we have quite a few more types. Type 5. This type has 3 more types. So 0/0, infinity 0. Again, these are all types. They're not powers, not exponents, they're all types. We will find the limit of the form of powers. It's possible when both go to 0. We have the type 0, f goes to infinity. The g goes to 0. The type or f goes to 1, g goes to infinity. A typical example for this one is try limit the positive side. So this we cannot plug in. 0 to the 0th power with it is 0, but I'm not sure the limit. Okay. So a method for this power is we use the change of basis. Change of basis. A to the B, E to the B. The B to the A is better, not A to B, because B for basis. B to the A. Change of basis. We can apply the change of basis to this function. We get okay, Sophia, what's the new exponent?
It is
Exponent A base logarithm B.
is e to the power of g of x ln f of x.
Yes. Change of basis. So this way, from the power to the exponent being the product of two functions. Then we go from the power, the product, we know how to deal with the product. And Sakina, let's convert this to the change of basis formula. What do you get? All right, because we want to find the limit of the exponent when x goes to 0. Well, how do you find this? How do you find this limit? Limit of the product. Okay, so we can go a little bit above. We just found it over there. It is 0. So we will use this information. It's this limit. Another type, infinity 0. Another one. The limit of this power base is x, exponent 1 over x. Okay, what we do to Zichen? Change of basis. Okay, so limit infinity e to the what's the exponent? 1 over x log x. So e to the limit, let's go to infinity, logarithm x over x. How do you find this limit? Okay, maybe check Sophia. Sophia, how do you find this limit?
You do
What method should we use?
L'Hopital.
Okay. Now, because when x goes to infinity, both numerator and denominator, they go to infinity. So infinity, so this will be a type infinity over infinity, so we can apply L'Hopital rule to the exponent. One over x and 1. Okay, so what's the limit of the exponent? Sakina, you want to say 1 over x when x goes to infinity? 0, yes. So this is e to the 0, which is 1. Okay, so wrong way. This limit is also 1. And there's something else. 1 to the infinity. 1 to the infinity. Let's try. Limit to infinity. Okay, let's go to 0 or infinity. 1 to the infinity. Let's go to 0. Make this simple. 0, 1 plus x, 1 over x. Okay, Sakina, how do you deal with this? What's the first step? Okay, change of basis. Change of basis. E to the Zichen, what's the new exponent? Okay, so now we want to find this limit. Logarithm 1 plus x over x. And Sophia, how do you find this limit? What's the type?
0 over 0.
0 over 0. Okay, so we can apply L'Hopital rule limit. Numerator is 1 over 1 plus x. Denominator just 1, so we can plug in e to the 1, which is e. quite a few limits. So you can see this L'Hopital rule it can apply to many cases, but you be careful. You always check if it's the right type. If it's not indeterminate form, then it's not applicable. Okay. Then we will give a summary, maybe not a summary. It's called the antiderivative. Next section, antiderivatives. So derivatives, we know how to take a derivative. Give a function f, we find the derivative. So this antiderivative is we go to the other way. We give some function. We want to find who the derivative is f. Okay, that's antiderivative. Okay, make a comparison. Derivative fx goes to the derivative. But antiderivative is something in the opposite. We give a function f. We want to find something whose derivative in this case, we will call this the antiderivative of f. Okay, so let me give a formal definition. A function. Very heavy. Definition. Give a function f, another function to make them different but closely related. We choose this capital letter F. It's called the antiderivative if the derivative is this function. A very quick observation. F is antiderivative. And general. Okay. So about the general antiderivative. So it's one antiderivative with an additive constant. You can add 1, add 2, -5. You have the same thing because when we take a derivative, the derivative of a constant, what's that? It's 0. Yes. Okay, so now let's check. We have a function. We want to find an antiderivative and then a general form. Okay, so we'll start with which one? Start with x, maybe 1. Okay. And Zichen, could you give me a function whose derivative is 1? How do you find that? Because you can take a derivative. Because we can take a derivative, we get 1. Okay. So the general one will be x plus c. Okay, and the Sakina, I want x. How could you give me an antiderivative for x? Something whose derivative is x. Not easy. Huh? Think about it. Okay, so something x to the some power, if we take a derivative, we reduce the power by 1. X to the 1, if we take a derivative, because x to the 0 is the constant. We want to get x to 1, what do we have? So something, if we reduce the degree by 1, we get a 1. So something subtract 1 is 1. Okay, it does the work? Almost. We have, if we take a derivative of x squared, what do we have? 2x. So we have to divide this by 2, then we get what we want. A small modification. Then the general will be x. Okay. And Sophia, x squared. Could you give me a function whose derivative is x squared?
X x cubed divided by 3.
Okay, x cubed, if we take a derivative of this, the 3x squared, we divide over them by 3, we get what we want. And the general one. And the x 3. Okay, so now we know how this goes. And make it a little bit more complicated. And the Sakina, x to the pi. So first, what's the power? Yes, nice. And what's the constant for corrections? Is the 1 over pi or something? Yes, very nice. The plus 1. Okay, so 1 over pi plus 1. Okay, now the general case, x to the a naught negative 1. Okay, Sophia, could you give me an antiderivative of this?
1 divided by a plus 1 times x to the power of a plus 1.
Mm-hmm. And here, this is why I excluded the case that x can be negative 1. Because when, oh, sorry, it should be a. I excluded the case that a not negative 1. Because when a is negative 1, the denominator becomes 0. This has to be excluded. Now let's focus on the case x negative 1. Okay, think about this. Second, what's the antiderivative? Okay, who has
log of x.
Okay, we have one candidate, log x. Okay, so for this one, it's correct, but we have to be careful. What's the domain of this function, Sophia?
0 to infinity.
So x positive. What's the domain of this function?
It's
Not 0.
negative infinity to 0 and then 0 to infinity.
Okay, so when x is positive, we have the antiderivative. What happens on the negative part? We want to extend our domain to the whole domain with the property whose derivative is x negative 1. We modify this a little bit. How do we modify this? How do we include the negative numbers? Okay, so we have done this before. This time we make a small modification. It's still logarithm. And we have checked this before. The derivative of this is, so you should know how to verify this. The derivative of absolute value. We have two parts, when x is positive and when x is negative. Because the positive, the absolute value, just logarithm x. When it's negative, logarithm, the absolute value becomes negative x. When we take a derivative, we apply the chain rule. So it's 1 over negative x, apply chain rule. Okay. So this function, the logarithm absolute value, we checked on the positive domain is 1 over x. On the negative domain, it's again 1 over x. So over here, we have the antiderivative on the whole domain when x goes to 0. And okay, next, a slightly easy one. E to the x. What's the antiderivative for this one? E to the x. So every time we want to find the antiderivative, we think about the derivative process. Okay, now a little bit change. 2 to the x. Okay, think about this. Let's have 5 minutes break. We'll be back at 52. Think about this. How to find the antiderivative. Okay, 5 minutes break. Okay, so let's continue. 2 to the x. Okay, how do we find the antiderivative? Any idea? No, okay. No, now let's go back. How do we find the derivative of 2 to the x? What's the derivatives? Anyone remember this? If not, how to find the derivative? We know the derivative of the exponential. How do we find this derivative? Okay, so both of you are correct. So you give the result and you give the method. So the method to find this chain of bases. Okay, so Jen, you said chain of bases. If we chain of to E was the new exponent. Okay, so now we apply chain rule e to the x logarithm 2, x logarithm 2. So now we can switch back. We can change the basis again. So this will be 2 to the x. And then what's the derivative of this? 2 variable log 2 coefficient log of 2. And this is what Skinner just mentioned. So that's the derivative. Okay, so we know that derivative something, if we put a logarithm, I'm sorry, if we put 2x over there, the derivative will be this with an additional factor logarithm 2. But we don't have it over there. How to change the function here to such that the derivative is just 2x, no extra logarithm 2. We have, all right, yes. If we take a derivative, we get an extra factor, so we divide it beforehand. This time, if we take a derivative, this will produce a logarithm to cancel with the one we designed, then we get this clean form. Okay. Okay. So next, okay, the general case. B to the x and the B is not B positive and not 1. Okay, what's the anti? Let me check with Sophia. Could you give me an antiderivative for B to the x?
It is B. Oh wait, it is 1 over log of B times B to the x.
Yes. Yes. Okay. So and in the very beginning, when I give you assignments, you may forget this factor. It happens. If it happens, you saw it, it's oh, I forgot it. Maybe after a few times, you will be familiar with this. You will never forget this extra factor. Because when you take a derivative, this term alone will produce a factor. We'll have to cancel them. Okay, now another class, fx, fx. We'll continue our work on this antiderivatives. Okay, maybe enough. Okay, so we go to cosine x. Okay, Zichen, give me an antiderivative of cosine x. Why? Because sine derivative is cosine. Okay, yes, that's a very simple explanation. Okay, Sakina, sine x. Okay, so yes, so you pay attention, so you have this negative cosine x. Because when we take a derivative of a cosine, we get a negative sign. Again, we have to cancel this factor. Okay, nice. Okay, you goes ahead of me. X. Okay, something not that easy. I go with secant square. Sophia, secant square. Okay, it's very special. 子承 secant and tangent. Okay, so this one, some memory is secant. Okay, now the real test. All right, very complete function. Sub one, so the derivative is this. Any big memory of this? Not a polynomial, not the sine, not the cosine, some inverse functions. Okay, what do you guess? Okay, Sophia, any idea?
No.
So some inverse function we learned before. This one will be sine inverse. Okay, so it's sine inverse. Another one, 1 over x squared. Okay, yeah, this is the first time I just want to test your brain. It's okay, it's completely okay. In a few weeks, you will know this at the top of your head. This will be tangent inverse. Now let me check. How did we find this derivative? What method? Okay, what are the steps to find this derivative? Sophia, any collection of this? So we use this method called the implicit differentiation. Okay, so to find this limit derivative, we introduce this dependent variable. Then from the definition, this is the same as sine y equals x. Now from the explicit function to an implicit function, because we know how to find the derivative of sine. From here, we take implicit differentiation. Get a cosine x, cosine y, a derivative equals 1. Then we know that since sine y is x, the cosine y, after some checking and simplifying, we get 1 over. Okay, now, how did you find this derivative of arctangent? Three of you, how do you find this? What method?
Implicit differentiation.
Uh-huh. You? Similar one, okay. Okay. So after this class, I want you to go back, or you can try to find the derivative yourself to verify this step. It's a good practice, and you will get this whole table. Okay, now a little bit more. Okay, let me test you. Anyone remember this function? What's the name of this function? How do we call it?
Hyperbolic cosine.
Okay, I have one response, and two of you. So I have this h. What does this mean? hyperbolic. Okay, for hyperbolic functions. Cosine h. So this hyperbolic functions. Okay, so we call this one hyperbolic cosine, this one hyperbolic sine. Okay, Sophia, what's the antiderivative of hyperbolic cosine? Something whose derivative is this.
Yeah.
Okay, we can check this one. If you take a derivative, how do you take a derivative of this one? E to the x, what do you get? E to the negative x. And so apply chain rule will be -1. So -1 cancel with each other, we get a positive. So if you take a derivative of this hyperbolic sine, hyperbolic cosine. So if we go backward, we get a hyperbolic sine. So hyperbolic is okay. So what's the antiderivative of hyperbolic sine? So something whose derivative is this. Okay, let's check. This one, if we take a derivative, Sakina, what's what's the derivative? What's the derivative of this one? Okay, see, if we take a derivative, we get exactly this. If we go back, we get the hyperbolic cosine. Okay, now if we compare the regular trig functions with the hyperbolic trig functions, they're similar, but there are some differences. There's no negative sign for this hyperbolic cosine. Because when we take a derivative, hyperbolic cosine, this sign stay the same. We flip this one, we get sign, not negative sign. Okay. Now some properties of this antiderivative. If we have two functions, okay, we found two antiderivatives. Could you give me an antiderivative for this one? Anti F 3D. Okay, what's your answer? Louder. So what's the condition we know? We know that the antiderivative f is capital F. We know the antiderivative of g is capital G. Could you represent the antiderivatives using capital F and capital G? To make it, let's make it more precise. So we know that the antiderivative of sine negative cosine f cosine sine. Now I'll give you 2 sine x minus 3 cosine x. Give me an antiderivative.
Negative 2 cosine x.
Plus or minus, I heard something. Minus. Okay, so what we observe is that the linear combination of the function give us the linear combination of the antiderivatives. So here the formula will be 2 capital F. Okay, let's try another one. Let's find the antiderivative. Okay, think about this. What's your answer? Okay, okay.
E to the power of x minus 2, minus 3, minus 1/2 x, 1/3 x cubed.
Uh-huh.
Plus,
Do the work. Uh-huh.
1 over log of 6 or log of 5 times 5 to the power of x.
Okay, so she gave us one antiderivative. Now we can check. If we take the derivative of this, we recover the initial function. Derivative this one. Derivative this one. So cube 1/3, they cancel each other. Derivative of this one. Okay, slightly more complicated. Now this is a function f. Sorry. Wrong function. F e to the 3x. Slightly more complicated. So how to find an antiderivative? Sometimes it's not easy to get this in one step. We will try a simpler one and try to modify it. Okay, the first step, give me a reasonable guess. What would you guess this will be? Doesn't have to be correct as long as it's on the right direction. Uh-huh. Okay, let's try this. Does it work? Okay, so what are we missing from this one? If we take a derivative of this, what do we get? Okay, we don't know if it works or not, but we can check. Ah, so bad. Rewrite my x. Okay, so what's the derivative? Chain rule. 3, very good. Okay, now what's missing from there? Yes, we're missing 3, we can put a 1/3 over there to kill this 3. You see? So in the beginning, we made mistakes. We all do, but we make corrections. Okay, so now we can make it correct. Maybe a different color. So we made an additional factor to kill this unwanted 3 over there. Okay, now we can do a little bit more. Let's try this. fx cosine 5x. So Kina, how do you find an antiderivative? Okay, so that first attempt, uh, let's sine 5x. Okay, so Sakina, what's the derivative of sine 5x? And chain rule, times 5, yes. Okay, so if this were the antiderivative, we would have a 5 over there. How do we kill this 5? Divide by 5, so we make corrections. Okay. So you see, that's how we find the antiderivative. We make a reasonable guess. Then we adjust this to make it matches the derivative. Uh, Another one. Another one. fx 2 equals 3x 4 cosine 5x. Let's find an antiderivative. Sophia, you can enter your answer in the chat. Let's open my chat. Bettina, do the work. You finished? Okay, great. Let me check. All right, okay. So she finished. That's all right. Sakina, check her work. Check her. Huh? You are my assistant. Okay. Yeah, you can check each other's work. So, okay, it's okay. Then compare. All correct. Okay. Maybe it's let me check. So this will be twice of the one over there minus 4 of this times. Okay, I think you entered this wrong. I think you mean E, but it's correct. Yes, that's correct. Okay, so 3 to equal 3x 5 4 cosine sine 5x sine. Okay. I think you mean some So I did something wrong, but you get the right answer. Okay, so now you can see finding this antiderivative is really based on how you understand the derivative. If you know how to find the derivative, you make a guess, then try to modify the guess to match the result. Okay, so you try and correct. Okay, so we had a few minutes. Now we will give a brief introduction of the next chapter about integrals. Okay, so the integrals 5.1 motivation for this integrals because of the area problem. Okay, we started with the basic one. If we have a rectangle, oh, I missed, not good. With base and the height, what's the area?
Base
Everyone knows?
power.
Okay, so base, height, a slightly more general. Oops. Again, I draw the height. Oh, that doesn't look good. Look good. Go with HB. Okay, Zichen, what's this area of the triangle? 1/2 BH. All right, next one. Okay. Sakina, how do you find this area? And then, okay, there's no formula for this. This is too general, even for this. Okay, then that's too easy. Then we make it more complicated. You said this, if it is a formula, then it's really? Eh, uh-huh. Okay, okay, and okay. So far from symmetric, kind of arbitrary. Yes, that's the point. I'll say there is no formula, but what we can do? Okay, so now I can go less crazy. Let's draw a reasonable one. Reasonable one. Make it not symmetric. Some longer, some shorter, different angle. Okay, it's kind of arbitrary. So what we do, we can partition this into triangles. Okay, we do the measurements. We find the area of this one, area of this one, then we add them together, we find the area. Okay, so this is called a partition. Go with A1, A2. Because each one of this is a triangle. That's not difficult. Okay, so this is the idea behind the method we will introduce the integral. Now we want to find the following. Now give a function. We start with some very special function, not very good, but is special. Ah, no. Nice. Okay, let me check with you. How do you find the area of this region? On the graph of this function. Okay, so Kina, what would you do? So Chen, what would you do? Okay, speed up. Okay, let's try. Okay, now so each part is much easier to find. We find this area, add them together, we get the area. So because the top, they are straight lines. Okay, maybe one more, but I forgot the last one. Another one is this. Okay, partition, measure, and the addition. Partition. This for some special functions. They are piecewise linear. Now, more general functions, what do we do? Okay, so now they have varying top. How do we find this area? We want to do the same thing. We want to make partitions, but there's no corner that we can make the partition. To make general partitions, this time what we start with approximation. We cannot find the area in one approach, so we use this approximation. Let's make some partitions. Okay, so for each of this, we approximate. There are different ways for this approximation. We can use a rectangle of the height with the left endpoint, rectangle of the height with left endpoint. So for each rectangle, we know how to find the area. We add them, we get one approximation. they will make better partitions. This will give us better approximations. So each time we make the partition finer and finer, we have better and better approximations. And in the end, the approximations will convert it to a number. And that number will be the area. So this is the idea behind the integral. So we will start with this next time, the integral. Okay, any questions? No? Okay. Sophia.